Welcome to our discussion on variation. As always, feel free to fast forward to the section you feel you need to practice. Let's begin with the simplest of variation, direct variation. You'll know it's a direct variation question when you see phrasing like y is directly proportional to x, or something varies directly with respect to something else. You'll normally see that word direct or directly somewhere in it. And when that is the case, you know that simply one number is equal to the other number times a constant. That's what this means, right? K is some non-zero constant. Simply you could have something like y equals 5x or p equals 1/2 q, etc. That's a q, by the way. Or m equals square root of 3 times c, right? Those would all be direct variations. Here's another example uh, where we want to find the equation, but we want to rewrite it in with k as a constant instead of just some number that we don't know what it is, right? It's just like when we have y equals mx plus b, the equation of a straight line. We always want to know what m is and what b is. So suppose y varies as x, right? That's another way that they'll write it. They'll just say varies as x. Varies as means varies directly. And they tell you y equals 20 when x equals 4/3. And they want you to find y when x equals 8. Okay, well, because it varies directly, we know we're dealing with the simple y equals kx. Then we plug in what they tell us. Y equals 20, right, when x equals 4/3. Do the math, i.e. solve for k by getting rid of the 4/3. So you multiply both sides by 3/4, and you get k equals 15. Now you can plug that back in and x equals 8. Right, so you've plugged in k equals 15, x equals 8, and you find that y equals 120. So now we know y equals 120 when k equals 8. It's that simple. Here's another example with a word problem. The current in a circuit connected to a 220 volt battery is 50 amps. If the current in the circuit is directly proportional, see there's that key word, directly, to the voltage of the attached battery, what voltage battery is needed to produce a current of 75 amps? Okay, so I decided to let I equal the current. You're thinking, why isn't it C? Well, in electrical engineering, they use I for current and V for voltage. And so we know instead of our generic y equals k, right, times x, we're just using I and V. We plug in what we know. They told us, if you don't remember, that when you connect a 220 volts, that's your V battery, you get 50 amps. 220 volts, right, 50 amps. This is I equals k times V. We want to solve for k. Can you see the first step is always to solve for k? Some simple math gives us 5/22, and you want to leave k as a whole number. Don't ever write this as a decimal because then you'll have to round, and you don't want to round. You want to leave it precise. So leave it as a fraction. This is now your equation. So now they want to know what voltage do you need to get 75 amps? Okay, well, in this equation, which one is amps? Remember, it's the I. So now we put in 75 for our I, solve for our V by simply just multiplying both sides by 22/5 to get rid of that fraction, and we get 330 volts. Next we have direct variation with powers. You're still going to see that they're going to talk about something varying directly to something else, but then they'll put in a phrasing about power, right? Y varies directly as the square of x, or as the cube of x, or even as the square root of x, things like that. And then it's simply still your y equals k times x, only now x is raised to a power. Here's a simple example. Suppose that you have forgotten the formula for the volume of a sphere, but you were told that the volume of a sphere varies directly, right, there's your varies directly, as the cube of its radius. And then additionally, you're given that the volume equals 972 pi whenever r equals 9, and then they want you to find the volume when r equals 6. So you plug in what you know. They tell you that the volume varies directly to the cube of the radius. So there's your v equals k times r cubed. Then you plug in that first bit of information. They told you it was 972 pi was the volume when the radius was 9. You solve for k like we always do in our first step, and again you leave it as a whole number. You don't want to make it a decimal, right? Leave it as 4/3 pi. Okay, plug that in as your k, and now you have the formula for the volume of a sphere, 4/3 pi r cubed. Now you can plug in the r equals 6 and figure out that it is roughly 288 pi cubic units, right? Cubic inches, cubic centimeters, cubic whatever the measurement for the radius was. It was 6 something, right? Could be meters if it was some huge sphere. Okay, now let's move on to inverse variation. So before was direct, now it's inverse. Something varies inversely as the quantity of something else, or y is inversely proportionate to x. Those are the ways that you'll recognize an inverse variation. It'll normally have the word inverse in it. And now instead of y equals k times x, it's y equals k divided by x. Here's our first example. Y varies inversely as x, and y equals 35 when x equals 11. Find y if x equals 55. So we start with our generic formula, we plug in what we know, and we solve for k. So far it's the exact same thing we were doing before. We get k equals 385. Now we plug that back in with the secondary bit of information, and in this case x equals 55, and solve for what we need. So there's our k. Then there's our x of 55, and we figure out that y equals 7. So you can see that the steps, the process of solving these is the same regardless of what kind of variation you have. The hardest part is going to be taking the English, right, the word problem, and looking at the words and figuring out which formula is it. Is it y equals kx? Is it y equals k over x? Are there powers involved? You know, what's going on? So you just need to look for those key words of inversely, directly, and a power of this, squared, cubed, things like that. Here's an example with powers. Y varies inversely as the nth power, right? So squared, cubed, etc. The intensity of light varies inversely as the square of the distance from the light source. If Rita doubles her distance from a lamp, what happens to the intensity of light at her new location? Same thing as before. The first thing you got to do is identify what kind of formula it is. In this case, it's the inverse with a power, so we know it's the general formula. The generic version would just be y equals k over x to the n, right? In this case, we're using I for intensity of light, d for distance instead of x, right? And they told us it was square, so we know it's a 2. And now we need to solve for k. But in this case, they didn't give us numbers. They just said, if her distance doubles, what happens to the intensity? So if we start with this original function here in yellow, and then we double her distance, well then now all of a sudden the distance is just 2d, which when you square becomes 4d squared. So your original equation was k over d squared, and it now became k over 4d squared. So what's happened to the new intensity? Well, if you can't see what that is, then you need to solve it algebraically. Right, so here's our original. This is what it was originally. Intensity was k over d squared. Now we have this new intensity, right? That's I sub 1. It's the new intensity with the new distance, and that was k over 4d squared. Well, if we want to figure out how that's changed, we divide it by where it started from, right? Like if it's doubled, then this number is going to end up equaling 2. This would be 2. If it's gone, down and now it's a half, then it's just going to equal a half. And we figure that out, we do its ratio, and if we divide by I on the left, we have to divide by I on the right, but instead of dividing by I, we divide by what I is equal to. A fraction divided by a fraction is the same thing as a fraction times its reciprocal, so you flip and multiply, and of course these cancel because they're the same. These cancel because they're the same, and you just get 1/4. So now if we want to figure out what's happening to I, we solve for it by itself by moving the I over, and it tells us that our new I was the original I divided by 4, or it is now 1/4 the original intensity. Okay, last but not least, how about joint and combined variation problems? They're just going to take the idea of direct and inverse and powers and put them all together. So z can vary jointly as x and y means it varies with respect to both x and y. So instead of just y equals kx, we now have this new variable z equaling k times the product of x and y. And then the same thing can be with powers. With powers of x and powers of y, you just get z equals kx to the n, y to the m, that kind of thing. Here's an example with Newton's law of universal gravitation. If you don't know the law of gravity or the constant of gravity that we have on the earth, you'll see how we derive it using this formula. Okay, we know that Newton's law of universal gravitation tells us that every object in the universe is attracted to every other object with a force that acts along a line that goes to the center of those two objects. So if you draw a line from the center of one object to the center of the other object, the force is pulling them together along that line. We also know that that attracting force is directly proportional to the product of their two masses and also inversely proportional to the square of the distance between them. So the heavier the objects are, the more they pull on each other, but the farther apart they are, the less they pull on each other. That's why it's inverse, by distance. So step one, we want to write this law in symbols. We're going to let m sub 1 and m sub 2 be the mass of the two objects, and r is going to be the distance between their centers. Always a good idea to draw a picture, and here's the picture. There's my first mass on the left, my second mass on the right. R is the distance between their two centers. We now know that if we let F be the actual gravitational force between those two objects, according to the question, it varied directly. Right? And directly is why we get some constant times them. And this is just our k. But instead of calling it k, we're going to call it g for a gravitational constant. And it varies directly as the product of the two masses, and then inversely divided by the square of the distance between them. Now g, this universal gravitational constant, we know is this big long thing. It's a very convoluted number, right, with this meters cubed per kilograms per second squared. Don't worry about it so much, just pay attention to the next slide. Okay, if we want to estimate the value of little g, the acceleration due to gravity. Remember, big G is this constant. Little g changes depending on the size of the two objects and the distance between them. So if we want to estimate the value of little g near the surface of the Earth, we're now just figuring out if you want to draw a picture, here's the Earth, and here's some object sitting on the surface, like you. Well, the gravitational member is going to go from the center of the Earth to the center of that object, and that's going to be your R. Okay, so F is going to equal, remember this is just our K in disguise, we're just calling it G instead of K. Mass of one thing, mass of another thing, distance between them. Okay, well the mass of one thing is just going to be some arbitrary item, right? So force, another way of writing force is mass times gravity. We all know that force equals mass times gravity. Of course we know that. If you didn't, that's no big deal. You get that from physics. So all we did here is we did a straight substitution. Force equals mass times gravity. And then all we did over here is change these kind of generic letters for the things we're going to be dealing with. The r, instead of just being some generic r, is the actual radius of the Earth. So this is r sub e squared. I know it looks kind of complicated. It's not e squared. It's this whole thing's being squared. And then this first mass is going to be the arbitrary mass, just of some object. That's why it's just an m. And then the second m2, right, is going to be the mass of the Earth. Okay, so now with all of those in place, we can see that we can cancel the two m's, because we have this arbitrary mass times gravity and we have this other arbitrary mass. Divide both sides by m, they're gone. Now we've got this simplified function. Remember, this is the whole thing squared. Okay, plug everything in that we know. We have the number for the gravitational constant, we have the number for the mass of the Earth, and we have the number for the radius of the Earth. When you put all that stuff in your calculator, you end up getting 9.8 meters per second squared. And if you didn't already know that, and if you've had physics, you do know it for sure, that is the force of gravity on the surface of the Earth. We know that if, for instance, if you drop something off of a building, gravity is going to pull it down at a speed of 9.8 meters per second squared. Actually, it's an acceleration because it's meters per second squared. But that's it. That's how we can deal with variation and indirect variation with powers, and Newton's law of universal gravitation is a great example of combining all of it together.